So let's move over now to orthogonality conditions. So when you talk of orthogonality in matrix, it has something to do with the product or a triple product of vectors and matrices that yields to a value which is an identity matrix. So same is true with the orthogonality on trigonometric manipulations, wherein the cosine of the expression will lead to a value equal to 1. And we know that the arc cosine of the angle that is equivalent uh, to 1 is simply a normal angle or a perpendicular angle that defines your uh, base axis, more commonly known as your three-dimensional axis. Okay, so if this is your orthogonal axis xyz, then the angle that defines such orthogonality is simply the angle 90 degrees. And take note that when we talk of directions in matrix format, we are referring to the direction in terms of the trigonometric function cosine. That's why we call it direction cosine. Okay, so if we talk of matrices in a form, let's say uh, this is the matrix of direction cosines, let's say A, we can actually make use of orthogonality condition in the form that the matrix would simply arrive at a triple matrix vector product that yields to the identity, which is simply 1. Okay, so this identity matrix defines orthogonality condition in this expression. So this is a triple product of vector and matrices, where A here simply is the matrix of direction cosine, okay, or simply a matrix that will define or produce the identity matrix I. Okay, so in that regard, this procedure is now used to further simplify the solution to MDOF system, since we are going to expect a higher multi-degree of freedom, wherein the mode shapes will be uh, larger than just uh, that shown in the previous example. So as we consider now two particular modes, R and S, on an MDOF system, we can say that orthogonality in this regard can be applied on the basis of the matrix M and the matrix K. And the objective of such determination is to yield what you call uh, uncoupled system. No? So we are trying to uncouple uh, the system for facility in the process of arriving at a solution. Because if we do not do that, mathematically it's almost impossible for the computer to handle a problem using a closed form solution. So here, these two equations here were derived from the formula uh, a while ago, which is simply k minus omega squared m multiplied by y equals 0. Okay, so if we multiply y there and y here and interchange the uh, the location from the left to the right of the equation, so we arrive with this simple equation wherein the two modes R and S were substituted as part of the uh, the equations to be solved. Okay, and if we have here a product which can be further converted into this form of a triple vector matrix product, we can simply multiply your y vector with the y vector ys transpose on both sides, such that your equation 1 will be yielding to an equation similar to equation 3, and equation uh, 2 will be uh, yielding to equation 4, uh, such that your orthogonality condition now will exist, may exist in such form. Okay, so again, our target is making it more simpler for us to solve the entire MDOF system. So if we make use now of a simple subtraction of equation 3 uh, and 4, okay, so we yield now with this general equation wherein the content or the elements of the matrix can be separated by simply assuming that there will be values where R and S will be equal and where R and S will not be equal. Okay, before we do that, let's look at this equation. So your omega R and omega S, assuming they are of different mode, cannot be equal to 0, okay, because they are of a different mode. And this part here uh, will only be 0, okay, will only be 0 if your R and S is not equal to 0, such that your 5a was derived from the fact that your R and S is assumed not to be equal to each other. They are of these different modes. Okay, but if, on the other hand, your R and S are equal or are the same, then this will yield a 0 value, and therefore this value on top cannot be 0. So it's a it's either this will be 0 and this not 0, or this will not be 0 and this becomes 0. So you have two possibilities in such assumption of modes R and S being equal or not being equal. Okay, so since your property of a triple product can be applied such that your R mode can be the one prem-multiplied for as long as it is on the transpose. Okay, so assuming that this is a vector, so ys must be a transpose vector. So we cannot multiply a vector with a matrix. Okay, let's say this is a 3 by 1. We cannot multiply it by 3 by 3. Okay, so because these are not compatible. Okay, so we can only make this transpose such that this becomes a 1 by 3 matrix, and this is a 3 by 3 matrix. Okay, so there's compatibility on the two subscript here, such that you need to only to transfer R on the right side and make it a transpose, and Y on the other side make it a transpose. So a transpose of a transpose is simply a normal matrix. Okay, so this is the meaning of these two equations here. And taking note that a simple relationship of y, okay, so y is the response, the actual response. What did we say? This is the actual response, and the phi is the mode shape. It's only the shape. Okay, but the shape is more important than the value, the magnitude of the response. This is the letter A that we are dealing with a while ago. Okay, so they are related in such a way that a C matrix excuse me, defined by the coefficient in which the mode shape were taken, you now get a similar orthogonality transfer from y to phi. Okay, so this is simply a mapping from y mapped to a phi matrix. So if this is orthogonal, in that regard, this must also be orthogonal. Okay, so orthogonality now applies not only on the response but also on the mode shape. And again, we are not interested yet with the response, rather we are interested with the mode shape, because the shape will dictate the behavior. Okay, it dictates the behavior of your structure, of your system. Okay, so this is just similar. Now, if you look at the orthogonality condition here and here, they are just similar. Now, to give you now the formal definition of what orthogonality property of a matrix is with respect to another, can be viewed as a triple product resulting to a matrix which is diagonal and uncoupled. So the diagonality will actually be pertaining to the uncoupling of our matrices. And uncoupling of matrices will yield to a simpler solution. From MDOF solution, we are now using n SDOF solution. Okay, so MDOF to N SDOF. If you have a 10 degree of freedom system, you are actually doing a solution of 10 independent SDOF solutions. So that is the objective of orthogonality, of inserting the orthogonality property here. So note that also Km are very symmetric in this case, very much symmetric because they are diagonal. And the phi matrix possesses, of course, what you call the orthogonality property. So remember what I told you a while ago, that the choice of the coordinate system is very important. Here, we don't have to worry about the choice, but rather phi will take care, okay, will take care of the choice. So phi will normalize, will make it solvable in terms of a simpler solution of 10 independent SDOF system. So from the vibrating beam problem, we note that by proper choice of coordinate system, the MDOF system may be converted into an independent SDOF system. So we try now phi, which is the transformation matrix, and hope to uncouple the system. So we are changing now the system from Y to Z, noting that your tool to the solution is by applying the mapping matrix or the transformation matrix in the form of your what's this again? The mode shape matrix. The role of the mode shape matrix is to transform your coordinate system to a better coordinate system that will take care of solving the 10 or the N SDOF system originally from the MDOF system. Okay, using the same procedure, which is prime multiplication above, we can now write this DEM into this form such that your equivalent DEM will now be in the form of an equivalent matrix MI, KI, and PI. So remember the first topic on getting the equivalent M asterisk, K asterisk, and P asterisk. So that's the major key to solving a solution of a complex system like the MDOF system. And to get the actual response, if we are now interested in the actual, we can go back by simply using the original transformation equation from Y to Z. We go now from Z going back to Y. So note that phi is a normalized mode-shaped matrix. M asterisk, K asterisk are actually identity matrix if we make use of what you call a normalization procedure. And the normalization procedure is such that your matrix, the mode-shaped matrix, which may be different in terms of values, can now be set into a single normalized value or shape or form by using the normalization equation of phi normalized of vector I is simply equal to the assumed mode shape, okay, or not assumed but the computed mode shape divided by the normalization factor square root of phi t m phi. Okay, so phi I t m phi I. So this is again an orthogonal matrix. So sometimes there's no need to normalize actually. You can solve it the way you as usual. You only need to normalize it just to make sure that the values may be simpler to understand in a form. Remember the response spectrum normalized shape wherein the acceleration is actually graphed or made to appear in terms of the gravitational acceleration 1.0 g. Okay, but the actual acceleration may not be 1.0 z. The actual acceleration may be different because of the different types of soil, different amplification factor influenced by the nearness from the fault line, etc. Okay. Okay, so this ends the orthogonality concept, and we will apply this concept on the later on actual problems in earthquake engineering. Okay,